All right, we're live on YouTube again. So this is the second part of lecture 2. Let me share my slides. All right, so today we're going to do a few more problems surrounding logic. Okay, so the first problem will roughly take you 2 minutes. My suggestion would be to pause the video and try to solve it by yourself, and then resume the video and see how I solve it. All right, so let P to be a variable representing the statement it is code, and Q be the variable representing the statement that it is raining. Now we would like to rewrite them using logic notations. Okay, so P is this code, Q represent it is raining. So it is not code, basically corresponding to the negation of statement P or proposition P. And the second one, it is code and raining. So we know that the first part is P and it is raining is Q. So this is the AND operation. So we have P and Q. Next one, it is code or it is raining. So this is going to be P or Q. Last one, it is raining or it is not code. So it is raining is Q. It is not code is negation of P. So it's going to be Q or not P. Okay. Sometimes you don't have to write the parentheses. So it's just this. All right. Okay. So this is just a repetition. Notice a slight difference here, but we know that a commutative rule means that those two things are the same, logically equivalent. So both are correct. Okay. All right, next one. So this one is quite interesting. There's actually two different ways to try to solve this. I'm going to try to solve it by just using variable x and variable 1 and put a bunch of condition on it. And then there's a different way to look at it too. So let's say, well, I have two variables, x and y. They are all real numbers. I would like to have a Boolean algebra expression. So if I just translate things directly, there's one way to translate. Let's say the first statement is both x and y are positive. So when I have variable x, it's positive is when x is bigger than 0, and y when it's positive is when y is bigger than 0. So the first one, I could technically write it to say, if both of them are positive, is x bigger than 0 and y bigger than 0, right? That's one way to directly translate this. And the second one is to say at least one of them is positive. So that means either x is positive or y is positive, okay? The third one is actually quite interesting, is exactly one of them is positive. So they cannot be both positive. So there's a slightly complicated thing. Again, this is where you can pause it and then think about how you would solve it. So the way I would try to write it, so exactly one of them is positive can be break down to two situations. One, only x is positive, and one is when only y is positive. So what does it mean when x is positive? That means x is bigger than 0. But then, of course, y cannot be positive. So and y is smaller or equal to 0, right? That's the first part. And then I can say this is when x is positive, or only y is positive. So that means x is smaller or equal to 0 and y is bigger than 0. Okay. So this is this piece here. Now the next one is to say neither of them is positive. So there's definitely different ways to write it. I'm going to use one of them. Neither of them is positive. So that means x is not positive. I can write it to say the negation of x being positive and the negation of y be positive. And alternatively, this is the whole statement is actually equivalent to x smaller or equal to 0 and y smaller or equal to 0. Okay. Of course, everything I've done so far is just, using those variables, and I'm spelling out the actually proposition itself. But another way I can do this for this problem is to say, well, I'm going to use P to represent the statement that X is positive. And I'm going to use Q to represent the statement that Y is positive. Then the first statement, when you say both X and Y are positive, is going to be the situation of P and Q, right? So both of them are positive. The second one is at least one of them is positive. It's going to be P or Q, okay? And I'm going to challenge you, take home, to study what the situation is going to be for 3 and 4 if I'm using P and Q to represent the statement X is positive, Y is positive. What is the corresponding expression for 3 and 4? Okay. All right, moving on. So this is sort of expanded version of a truth table. The idea is I would like to prove if this statement and this statement are equivalent. One way to prove it is to show that in the truth table, their corresponding columns are exactly the same. Another way to do this is actually to show that, through the statement, theorem 2 from part 1 of the lecture, and use all those substitutions to show their equivalent. We're going to go through an exercise later. But here, let's look at the current example. Again, I would pause the video and try to solve it on your own, and then resume the video and to see how I'm doing it. Okay. So now I kind of make this problem a little bit easy because I have already filled most of this column. The only thing I need is those 2 empty columns. Okay. So the first row, I would like to decide, I'm focused on right now this column. Okay. So this column has 2 parts, P or Q, and then Q or R. So since both of them are true, I have, since it's an AND operation, it's true. So if it's an AND operation, I only need to focus on the 4th column and essentially the 5th column. So in this case, the second row, true and true is true. Third row, true and true is true. Fourth one, true and false is false. True and true is true. True and true is true. False and true is false. And false and false is false. Okay. Now, in order for me to judge the last column, I only need to focus on this pink column and the second column. So again, I'm going to look at, again, this is an OR operation, means that it's true when at least one of them is true. So the first row, I have true or true, that's true. Second row, true or false is true. Third one, false and true is true. Remember, right now we're paying attention to only the pink columns. The fourth row, false and false. False or false is false. The fifth one, true. Next one, true. Next one, false or false is false. And last one is also false. Okay? So now we have decided that those 2 things are logical equivalent because the 2 columns I just fill out are identical. Okay? And this is, just a repetition from the previous slide. So you can check your answers. So just to recall, what is De Morgan's law? Okay. So De Morgan's law has 2 parts. The first part is that if I put a negation between 2 OR operation, let me use lowercase. And then 1 is put negation over AND operations. So remember, the important part for De Morgan's law is to flip the arrow's direction when you do the negation. So in this case, if I take the negation of P or R, this is equivalent to taking the negation of P, taking the negation of Q, and then flip the direction. So this is what you get. The second one, if I bring the negation in, negation of P, negation of Q, again, I flip the arrow, so became all. So that's it. So this is just a quick review. Here I'm using uppercase to represent propositions. So now let's do some practice problem. You can pause the video now. It's going to take you roughly 3 minutes. The idea is to use De Morgan's law to rewrite the statement such that the negation sign does not appear outside of the parentheses, okay? So the way to do this actually for both problems, actually for the first problem, there's actually 2 different ways to do it. They all lead to the same answer, but it would be interesting to think about 2 different ways to try to solve the first one, okay? So let's do it one by one. Okay, so first one, the way we're going to do it, the idea is to try to bring the negation sort of layer by layer, but it's from the inside to outside. So in this case, because I need to apply De Morgan's law, so I'm going to look at the first negation symbol that is, I would like to bring inside the parentheses. So it's going to be this one. This is the negation sign I want to focus on. So if I do that, I'm going to first copy the outside negation symbol. I'm not going to touch it. I'm just going to operate on what's inside. So I'm going to operate on what's yellow. So when I bring this inside, remember, whenever I bring the negation inside, I need to flip the arrow direction. So if I bring it inside, I'm going to write this step by step. If I bring this inside, this became negation of P, and then negation of Q. And then because I'm bringing negation inside, the AND operation become an OR operation. So that's what I have. If I simplify a little bit, I get negation of P is P itself. And I get this, okay? So once I have this, what I get is now I'm going to focus on bring the negation, take the outside negation. So I'm going to do this whole thing now. Again, apply De Morgan's law one more time. So because I'm going to bring negation in, so negation of P and negation of Q, okay? And because I'm bringing negations in, I need to flip it one more time. So I get negation of P and negation of Q is Q. So that's my final answer. Alternatively, I have another solution here. What I would do is I would define a variable R to represent the proposition negation of P and Q. Then the statement on the left-hand side is going to be simplified to negation of R, okay? If you look at negation of R, it's a double negation. If I'm using double negation, I get the variable itself. So what is the variable? The variable itself is negation P or Q, okay? So those are 2 different ways to actually bring negation inside, okay? All right, now let's do the next one. This one, if you look at how many negation symbols is outside the parentheses, there's only one, so I only need to operate on this one, okay? So I'm going to bring negation inside. So there's 2 variables. There's a variable P, and then there's this variable P or not, a Q or not P, okay? So if I bring it in, I have negation of P and then negation of the second variable, negation Q or not P. And then I need to flip the arrows. Okay, so now become OR operation. So the first part don't change. The second part, now I have this negation symbols right here. Now I need to bring it in, so I have negation Q and negation of negation P. Okay, so if I simplify it, this is what I have, because negation of negation P is P itself. Okay, so that's it. So now I have reached a state where there's no negation symbol outside the parentheses. Okay, so that's a quick review of the final answer if you're solving this on your own. So now let's quickly review what is a tautology. Okay, a tautology is a proposition that is always true, and a contradiction is a proposition that is always false. Okay, and tautology, we always use the symbol T, and contradiction, we always use the symbol C. So now let's look at truth table again, right? Remember I said tautology is the one that is always true, and contradiction is the one that is always false. So the first thing I need to decide whether the first proposition here, whether it's a tautology or it's a contradiction or neither. So we just need to complete the truth table. So again, this truth table, most of them has been filled out. We need to just focus on the last column. So in order to focus on the last column, it has variable P. It has a second piece here. So basically I need to look at the first column and the fourth column, and that's it. And it's an OR operation. So as long as one of them is true, I get true. So true and fourth is true, true and true is true, false and true is true, false and true is true. So because it's always true, this is a tautology. Now let's focus on the second one. So the second one, let's break it up into two parts, P and Q and negation of P or Q. So that is going to be the third column that is already filled out for you, and then the fifth column. And it's an AND operation, which means it's only true when both the variables are true. So in this case, true and false is false, false and false is false, false and false is false, and false and true is false. So this is always false. That means this second statement is a contradiction. Okay. Now you might ask, what about the last column? If it's a mixture of true or false, then it's neither a tautology nor a contradiction. Okay. All right, so we are going to be using theorem 2 to prove logical equivalence. Again, this is a quick review of all different rules that belong to theorem 2. Again, as I mentioned before, the ones that is most tricky to use is distributive and then De Morgan's law. Okay, so let's start from this is an example we have seen before. So again, I would encourage you to go over this simple example, and we're going to move on to a slightly more complicated one. But the most important part when using substitution rule is do not skip steps, especially do not forget about commutative and associative rule. Sometimes we just apply those rules automatically, but then what's resulting when you actually try to prove things, you're actually skipping a few steps. Okay, so try not to skip any steps. So let's start from the first one. Again, this is a time where you can pause the video and try to solve this on your own. And in the next slide, we're going to do this step by step. But it's very important to try to solve this by looking at theorem 2, which is listed on this page, and see if you can prove the logical equivalence by using some of those rules. Okay, this problem itself is actually non-trivial. There is a very tricky first step. And you are going to be sure that this is a question likely going to show up on quiz. Okay, so now hopefully you have tried this problem. Let's do it together. Okay, So in order to prove logical equivalence, I'm going to move from left to right. Okay, and then each time I'm going to apply a rule. I'm going to try to, let me move this to the right. Okay, I'm going to try to write out what rule am I using. So to prove logical equivalence, I'm going to just, first of all, copy the left-hand side. Okay, the goal is to use the rules one by one until I reach the right-hand side. Okay, so left-hand side, I have this. The first thing I could potentially do if I look at this is, okay, there is actually a negation sign that is outside of parentheses. So the first thing I might want to try is try to use De Morgan's law. Okay, so I'm putting the name of the rule on the right-hand side. If I use it, I'm just applying it to this entire piece here. So if I bring the negation inside, I will get negate not P and not Q. So again, remember, it's very important to pay attention that the arrows switch direction. Now this looks like I have not P and not Q, or not P and Q. So the next thing, this is probably the hardest part for this question. If you look at this, which rule does it looks like? Okay, I have 4 terms on the right-hand side. If I want to simplify it, what rule can I use? So this is actually using distributive rule. Okay, so it's actually, if you look at it, it actually looks like the right-hand side of this formula, and I'm going to bring it to the left-hand side. So it's essentially sort of factor out a particular term through the distribution. So this is distributive rule right here. So now I'm going to have a shared term, which is not P. I'm going to bring it outside. And of course, it's an AND operation because I have 2 AND operation here. And then since I factor it out, what's remaining? It's an OR operation. Okay. So this is by applying the distributive rule. Okay. So the next thing, now I have a distributive rule. What's interesting is if you look at this term, this is negation of Q or Q. And this looks familiar, right? Because this is going to be the, well, there's a few things you can do. First of all, if I want to be, exactly the rule as I want to use, I can switch the order of this two. Q, not Q. This is basically applying commutative rule. And now next thing is, now I have the form Q, not Q. This looks like Q or not Q. This is going to look at the negation rule right here. Okay, so now I have applied negation rule. And when you have a variable Q and not Q is always true, so I have negation of P and tautology T. It's always true, so this is using negation tool. Finally, I'm going to use identity rule. If I have a variable and true, it's dependent on the truth value of the variable itself. So this is identity rule as below, right here. Okay. So of course, there is not guaranteed to be one single solution. Sometimes you might have multiple different solutions to try to prove equivalence. And then you will eventually prove the equivalence not through this order. So it's an interesting thing to see if there's different ways for you to prove it. Okay, so this is a recall of rule. So now let's throw in a question from number sequence. Number sequence, you learned it from lecture 1, part 2. But here is an interesting question. If I give you a sequence with a closed formula, an is 3 times 2 to the power of n minus 1. Is it true that the recursive formula is given below? Okay, so what is the main idea here? The main idea of this problem is to try to derive the recursive formula, from the closed formula. Okay, so that is the main idea. If you give me a closed formula, if I can derive a recursive formula, I want to see if the recursive formula I derive is equivalent to the one that is provided. Okay, so in order to do that, let's say, okay, because you're giving to me of the closed formula, an is equal to 3 times 2 to the power of n minus 1, then the first thing I do is to say when n is equal to 1, what is my a1? Okay, a of 1 is equal to 3 times 2 of 1 minus 1, which is 3 times 2 to the power of 0, which is equal to 3. Okay, so if I'm using the closed formula to derive the first term of the recursive formula, the first term, a1 is equal to 3. Okay, so that's the first thing. Now, because if I want a recursive formula, I want to understand the relation between an and an minus 1. So what would I do? So again, I'm saying an is equal to 3 times 2 to the power of n minus 1. If I using the closed formula, I have an minus 1. I substitute n minus 1 in there. So that is an minus 1, which is equal to, depends on how you want to write it. For the time being, I'm simplifying it. This is 3 over 2 times 2 to the power of n minus 1. Okay. I guarantee you there's a reason for me to write it this way. Now, if I take the substitution of this equation, star equation, and this equation, then an minus 1 is equal to 3 times 2n minus 1 minus 3 over 2 2n minus 1 is equal to 3 over 2 2n minus 1 is equal to an minus 1. Another way to say this is an is equal to 2an minus 1. Okay, so now what did I get? I have derived, first of all, for a recursive formula, the first term is a1 equal to 3. And for any subsequent term, an is equal to 2 times an minus 1. And that's exactly what's given here. That means the recursive formula given is correct. All right. So there's a very important point why I want to prove whether the statement is true or false, is that, well, we can show it false by demonstrating that the resulting sequence do not match. However, we cannot show the statement is true by just comparing sequences, because this formula gives the infinite number of points in the sequence. If you're only listing a finite number of elements in the sequence, you can't prove they're always equivalent. So the examples I showed here is actually proving by algebra. Okay. All right, let's end. Oh, let's do 2 more practice problem. So again, you can pause the video now and try to solve this on your own. Here is to use De Morgan's law to rewrite the following thing so that the negation does not appear outside. So again, if you start this problem, you say, okay, which is the negation operation I'm going to pay attention to? It's outmost one. I just bring it inside. So in order to bring it inside, I have, I need to bring it to 2 parts. The first one, the second one, treat them as variables. So I bring negation of P, and I'm going to do negation of Q, not P. This is actually something we just did. So this is just a quick practice. Okay. And now we are done. Okay. Next one. This is to prove, again, logic equivalence by using theorem number 2. Okay. So again, what we need to do here is to figure out what is the first rule we want to use? So let's start from the left-hand side. So left-hand side, I'm just copying it. Okay. The first thing, maybe what I want to do is to switch the order. So this is what's called commutative rule. If I switch the order between the OR operations, it's still equivalent. But when I switch this order, it gives me a little bit better view of what's going on. And now I switch the order. Next thing I do is, okay, this might be a good candidate for distributive rule. So this is right here, right? So I'm actually going to apply this distributive rule. So if I bring in distributive, so I'm going to do not P or P, and, well, let's see. Yes. Right? No, actually, let's be a little bit careful here. Yes. Not P or Q. Okay. And then and is in the middle. Now, because the first term here is not P or P, you can use now negation rule, because now this is equal to, it's always true, equal to tautology. Did I get something right? Okay. And now, because this is tautology and a statement, now we are going to use identity rule, because T does not influence the ending result. So it's always a truth table for the second variable. So that's it. Okay. All right. So I will see you on Tuesday's recitation sessions. And then you should also attend the discussion sessions where you'll have more practice problem for logic. All right. Have a good day.